All right, today you will be learning about graphing linear and absolute value inequalities. So graphing linear inequalities is review from Algebra 1. Absolute value inequalities is reviewing how to graph an absolute value function, and then graphing an inequality, very similar process to graphing the linear inequalities. So first we're going to focus on linear inequalities. And what it explains at the top here is that a linear inequality resembles a linear equation, but with an inequality symbol instead of an equal symbol. And it gives an example there. So y is greater than negative 3x minus 2 is a linear inequality. The equation would be the related linear equation. So the graph of this specific linear inequality is shown here at the right as the shaded region. So every point in the shaded region satisfies the inequality. That's important to note. Every point in the shaded region is a solution to the inequality, would be another way to phrase that. The graph of the related equation, y equals negative 3x minus 2, is called the boundary of the region. So for this specific example, it's drawn as a dashed line to show that points on the line do not satisfy the inequality, and that's because in the inequality the symbol is just greater than and not greater than or equal to. So if the symbol was less than or equal to or greater than or equal to, the points on the boundary would satisfy the inequality, so the boundary would be solid. So just as a note, if you have a less than or greater than symbol, you would use a dashed or a dotted line, and if you have less than or equal to or greater than or equal to, use a solid line. So we will get to an example. So example 1 is to graph the linear inequality x plus 4y is greater than 2. And the first step is to graph the boundary, which is the related linear equation. So that would be graphing this as if it was just an equal sign there. And when you graph the boundary, you want to make sure that your inequality is in slope-intercept form, y equals mx plus b, so that you can identify your slope or your y-intercept and your slope to make your graph. So I'm just going to rewrite the inequality. And in order to get it into slope-intercept form, I need to solve the inequality for y. Get the y by itself. So to do that, I first need to subtract x from each side. So 4y is greater than, and I'm going to write the negative x in front, and then plus 2 because it's positive. And then I would need to divide both sides by 4, and that means when I divide the right side by 4, I'm dividing both terms, by 4, not negative 4 there, that was my mistake. So there the 4's cancel, y is greater than. Now here, negative x divided by 4, there is a 1 in front of that x, so it's negative 1x over 4. So make sure you're not writing this as negative 4x. It would be negative 1/4 x. And then plus 2 divided by 4 is 1/2. So you can either write 1/2 or 0.5. So that is our inequality in slope-intercept form. And now to graph the boundary, I'm graphing this just as if it's an equation. So when I graph this, I can identify that my y-intercept b is 1/2, so I can put a point at 1/2 on the y-axis. And then the slope is negative 1/4, meaning from my y-intercept, I can go down 1 and right 4, or I could go up 1 and to the left to plot some additional points. And then to actually graph the boundary line, I need to make sure I look at my inequality because it's greater than and not greater than or equal to. I need to make sure that my boundary is dashed or dotted. And just do your best to Mine's not very straight. I'm just going to move my paper here. But just do your best to draw a straight line or use a straight edge if you have one. So that would be the boundary. And then step 2 is to figure out which half of my coordinate plane I need to shade, which half represents my solutions. So to figure that out, I can test a point and then shade. And testing a point means you're just choosing any point that isn't on your boundary line and substituting those x and y coordinates into your inequality to see if it's true or false. So the easiest point to test if it isn't on your line is 0, 0, is when both x and y are 0. So testing this again means in my original inequality, so I'll just rewrite that here. I substitute or replace the x and the y both with 0 and then see if the inequality is true. So I would have 0 plus 4 times 0 is greater than 2. Figure out if it's true. On my left side, this just becomes 0 plus 0. So 0 is greater than 2, and that is false. 0 is not greater than 2. So because it's false, identify which side of your line 0, 0 is on, and it happens to be below the line. And that means all of these points below the line are not solutions because 0, 0 is false, so I need to shade the other side. So if 0, 0 would have been a solution, I would have shaded the side that it was on. All right, and that is how you graph a linear inequality. So make sure, again, you're getting your inequality into slope-intercept form, graphing the boundary, and pay attention to whether or not it should be solid or dashed, and then testing a point to determine which half of your coordinate plane to shade. So then example 2 is now an application using a linear inequality. So we have a recreation center offers various 30-minute and 60-minute art classes. The recreation director has allotted up to 20 hours per week for art classes. Part A says to write an inequality to represent the number of classes that can be offered per week and then graph the inequality. So in order to write an inequality, I need to define some variables. So I'm just going to use x and y, and I'm going to let x represent the number of 30-minute classes, and then y represent the number of 60-minute classes. And what I need to recognize with this before I actually create my inequality is the classes in terms of time are given in minutes, and then the total allotment of time is given in hours. And I want to make sure that both units of time are the same. So I'm going to use half an hour for the 30-minute class and then 1 hour for the 60-minute class to make sure all of my times are in hours. I could have also changed 20 hours into minutes, but this way I'm dealing with smaller values by changing it to hours. So to write an inequality, again, I'm representing the number of classes that can be offered per week based on the allotment of time. So that would look like the following. I would have 1/2 x, so half an hour times the number of 30-minute classes, plus 1 y, or just y, so plus 1 hour times the number of 60-minute classes. And the director has allotted up to 20 hours per week, so this cannot be more than 20 hours, but it could equal 20 hours. So this needs to be less than or equal to 20. And this would be the inequality. Now I need to actually graph this. So this is actually writing the inequality. That's part of my answer. The graph is the second part. I certainly could get this into slope-intercept form to graph the boundary like I did for number 1, but I want to review with you another way to graph is I can graph this using intercepts. So this is the method that we reviewed in lesson 2.2, finding the x and the y intercept before you graph. So as a review, to find the x-intercept, Remember, this is where I substitute in 0 for y, and then I solve for x. And when I do this, I'm going to replace the inequality with an equal sign again because I want to know what that intercept actually is. So I would have 1/2 x, and then the plus 1y, this would be plus 1 times 0, so that's just going to be 0. So I have 1/2 x and then equals 20. And then to solve this for x, I could divide by 1/2, or I can multiply each side by the reciprocal, 2/1. So x would equal 40. So that's my x-intercept. And then the y-intercept, this is where you replace the x-coordinate with 0 and then solve for y. So if I replaced x with 0, this 1/2 times 0 would just be 0. So I end up with just 1y, or y, is equal to 20. And that's my y-intercept. Now, part of the reason I chose to graph using intercepts is this is actually going to help me create a scale for my coordinate plane so that I am able to see both intercepts on my graph. So that for this type of problem, that's part of the reason I chose that method. Along with a lot of students forget that this is a method they can use to graph other than slope-intercept form. So I'll call this 0. So again, this is 10 by 10. So if on the x-axis, I want to make sure 40 is on there. So I'm going to count on the x-axis by 5s, because that'll bring me up to 50. And then on the y-axis, I want to make sure that I see 20. So I could really count by 2s, and then 20 would be at the top. I think I'm just going to count the y-axis by 5s as well, because then for sure I'll see 20. I'll see higher than I need to, but that's okay. I'm going to skip over 40 just because I'd be writing over that word intercepts there. So there's my scale. And now to graph this, I can plot both the x and the y-intercept. So remember this x-intercept of 40, these are two separate points. So this is the ordered pair 40, 0. X is 40, y is 0. This is the ordered pair 0, 20. X is 0, y is 20. So a point at 40 on the x-axis, 20 on the y-axis. And then to draw in the line, again, make sure you check your inequality symbol. It is less than or equal to, so I do want to use a solid line for this one. And I can actually just connect these because anything, I guess, through either end of the intercepts is going to get you into either negative x or y values, which in this instance wouldn't make sense. So I can just connect them, not have to draw an arrow through either end. Then I have to determine where to shade. So am I going to shade in this triangle here, or am I going to shade above that line? And since 0, 0 is not on my line, I can still use that as my test point. So I'm substituting 0, 0 into my inequality. If I replace both x and y with zeros, my left side is just going to be 0 plus 0. So I would have 0 is less than or equal to 20, and that is true. So I want to shade towards 0, 0. So I would be shading in this triangle. And that would be the inequality and then the graph of the inequality to represent this situation. So then part B says, can the recreation director schedule 25 of the 30-minute classes and 15 of the 60-minute classes during a given week? Explain your reasoning. There's a couple of ways to find this. One way would be to use the graph. So remember that any point that's in the shaded region is a solution. Any point not in the shaded region is not a solution. And then also, because this line is solid, any point on the line is a solution. So if I have 25 of the 30-minute classes, that means my x-coordinate is 25, since x is the number of 30-minute classes. And then if I have 15 of the 60-minute classes, my y-coordinate is 15. So I really have the ordered pair 25, 15. Oops, 25, 15. So I can plot this point on my graph. So I have here 25 and then, let's see, 25, 15 would be right here. And when I plot that point, I can see it is not in that shaded area, and that tells me it is not a solution. So therefore, the answer to this question would be no. So I can say, can the recreation director schedule 25, 30-minute classes, 15, 60-minute classes during a given week? No, because the ordered pair 25, 15 is not a solution to the inequality. And I'll just put the inequality here. 1/2 x plus y is less than or equal to 20. I could have also explained 25, 15 lies outside of the shaded region, therefore it's not a solution. Another way to actually check this without looking at the graph would be to substitute 25 in for x and 15 in for y, and then see if that inequality is true. It turns out this side would actually be greater than 20, so it wouldn't satisfy the inequality. So there's a couple of ways to check. All right, the last example I have for you is now switching to absolute value inequalities. And graphing these is, again, like I said at the very beginning, a very similar process to graphing a linear inequality. You are first going to graph the absolute value equation, the boundary, and then determine whether that boundary is solid or dashed, and then test a point to determine which region should be shaded. So really the same steps, it's just now you're not graphing a line, you're graphing an absolute value graph, which is a V. So looking at example 3, with absolute value inequalities, before you graph, you need to make sure the y is also alone. So just like with the linear inequality, you want to get y by itself first. So to do that, I would need to subtract 4. Now make sure when you subtract 4 on the right side, so I'm going to have y is less than or equal to, I'm not subtracting 4 from this minus 2 here because that's inside the absolute value bars. So the minus 4 is going to be on the outside. So I have the absolute value of x minus 2 and then minus 4 at the end. So this is the inequality that I'm graphing. So if y is not by itself, get y by itself. Then you're graphing this as if it was an equation. So this we had reviewed in 2.6b to be exact. So as a reminder, you can graph an absolute value equation using a table. It's easiest when you're setting up your table for your x values to know where the vertex is going to be. So to find the vertex, you take what's inside the absolute value bars, so in this case that's the x minus 2, and you set it equal to 0. So this is to find your vertex. And then you solve this for x, so I can add 2 to each side. So my vertex is when the x-coordinate is 2. So I'm going to add that to the table towards the middle. I'm just going to put a v here, that's the vertex. And then I know I can choose values on either side. So I'll choose 1 and 0, and then 3 and 4. But this will make sure I actually do get a v as I'm graphing. And then I substitute these values in to find the y-coordinates. Again, I'm just thinking of this as an equation for right now. So when x is 0, I have 0 minus 2 is negative 2. The absolute value is positive 2. Minus 4 is negative 2. When x is 1, 1 minus 2 is negative 1. The absolute value is positive 1. Minus 4 is negative 3. When x is 2, 2 minus 2 is 0. Absolute value is 0. Minus 4 is negative 4. When x is 3, 3 minus 2 is 1. Absolute value is 1. Minus 4 is negative 3. And then last, when x is 4, 4 minus 2 is 2. Absolute value is 2. Minus 4 is negative 2. So I can plot these points And then when I draw my absolute value graph in, again, look at your inequality. It's less than or equal to, so this V is going to be solid. And make sure you are drawing the V completely through your coordinate plane. Because what happens with the absolute value graphs is now you have two parts to your graph. You have the part that's above or kind of inside of your V, and then the part that's outside of it. One of those two parts we have to shade. So to determine where to shade, you can still test a point. Still, I would test 0, 0 as long as it's not on your absolute value V, which this one is not, so I can test it. So if I substitute in 0 for both the x and the y, and I'm going to substitute it back into the original, just in case I wrote something wrong here, I'm going to test it back in the original. Usually, sometimes switching signs takes place, and if you forget to do that when you rewrite, then when you test a point into the one you rewrote, it's actually wrong. So just get in the habit of testing in the original. So I would have 0 plus 4 would be just 4 is less than or equal to, and then the absolute value of 0 minus 2, so the absolute value of negative 2 is really just 2. So I get 4 is less than or equal to 2. That is false. So I notice where 0, 0 is. It's inside of the absolute value graph. It's not a solution, so I should shade everything on the other side, so everything outside of the absolute value graph. And that is how you graph an absolute value inequality. Very similar process. So your assignment is included at the bottom here. It is all odds. There is an assignment sheet. So that includes the grids for you to make your graphs, but you still need to look in the book to see what the actual problems are. And then all problems are odds, so the answers are included in the back of the book on page R27.